Alright, so this is part 2 of the analysis of this truss. For the first part we calculated the reactions, and now what we're going to do is conceptually cut the truss open near the middle here, and we'll do the analysis. So first off, what we want to recognize is this is one way of identifying the truss joints and members by using letters. So here I have A and B at the two supports, C, D through J on the joints, and so each member is identified by the joints on either end. So for example, this is joint or member CD. So my conceptual cut is through the members that I want to find their forces of. So if I were to cut the truss open at this point, in order for this to be stable as a free body diagram, what I would have to have is external forces that replicate the internal forces. They act as loads, as a matter of fact. The internal forces become loads on the free body diagram. So I've got some loads out here, the vertical reaction. Got a load of 10 kips up here. Got a load over here of 4 kips. Then I have, in order to stabilize the structure, I'm going to have a force here, P of GH, of an unknown value, and P of CD, also of an unknown value. My guess is that those are going to be compression on the top and tension on the bottom, simply because when we gravity load something, the top is going to compress, the bottom is going to pull apart. So that's what those are. Then we have a diagonal member here, also that's cut through. And I'm going to guess that that is a tension reaction, again, because this is sort of arranged like a net. It's kind of catching everything. This is the organization of what's known as a Pratt truss, and typically these members are in tension. Now, the members that are internal to the section cut, these ones over here, we don't even need to worry about those because they're not being cut through. We can't find any of the forces. What we're really interested in is this free body right here. It's the loads and actions. Everything that happens inside of this boundary is internal to the structure. We're only interested in these external loads and forces. So let's redraw this. If we consider where do we want to actually do our moment sum at. So we want to try, and if we have a moment equation, we can only answer one unknown. So I want to find a place that will make other parts of the calculation go away. So I'm left with one unknown. And so if I'm solving for the top member, GH, a place that I could use is actually this joint D, because the line of action of this force and the line of action of this force, both unknown. So this, I didn't label it, as P of GD, also unknown. But they pass through point D, so if I sum moments about this point, both of those would go to 0 anyway, because there's no moment arm relative to point D. So let's draw this now as a series of forces and lines of action, because that's all that this is really about. So these are lines of action for the forces. All of the forces fall along these lines of action. And so our moment center is going to be down here. This is D, joint D. And I know that I've got 10 kips out here. I've got 4 kips here. Left vertical reaction, 14.5 kips. Now the force, there is a force along this diagonal, and there is a force here, but both of those go away. So that leaves this force, P of GH, unknown force, as the only unknown. Now let's put on some distances. Relative to point D, got a distance of 10 feet here. The 14.5 kip force, let's also put a parallel line through here. 14.5 kip force has a moment arm of 10-20 feet. And notice that this is off of the cut, right? It's outside of the boundary, but it doesn't matter where we sum moments. As long as we can get rid of one of the unknowns, that's where we want to sum the moments. Or we want to get it down to one unknown. So we have a vertical distance of 5 feet here, and also 5 feet over here. So now this very complicated looking problem has reduced quite a bit. So we're going to sum moments about joint D. So I always say where I'm summing moments about and what direction I call positive, so I don't forget. So I'm looking at all of the forces and rotational tendencies about point D. I see that my GH, I think, is going to go this way. Now, if I got a negative number, that would say that I've got the right magnitude but the wrong direction. So we're going to make a guess, though, that it's going to be compression this way. The 10 kip wants to go counterclockwise. The 4 kip wants to go clockwise. 14.5 similarly wants to go clockwise. So let's start with the 14.5 kips. At a distance of 20 feet. That's its moment arm. Then 4 kips at 5 feet. Both of those are positive because relative to D, they would have a clockwise rotational tendency. 10 kips at 10 feet. Now it's important to note here this is not negative because it's a downward force. It's negative because the rotational tendency relative to D is counterclockwise, and we're calling clockwise positive. So that's a negative sign. And also GH at 5 feet is assumed to be negative. So that comes out to 0 when we put that all together. So P of GH is going to be, calculator out here, 14.5 kips times 20 feet, 290 kip feet. 4 times 5 is 20. And then we have a, oops, minus 100. And that's all going to be divided by 5 feet. So 290 plus 20 210 divided by 5 feet comes out to 42 kips. So let's put that on our solution up here. Now CD actually turns out to be quite a bit simpler because CD eliminates, when we find the moment center that we want to use, it eliminate a lot of stuff. So we're looking for this force. We know that one. We also don't know this one. So wherever the point is that we pick, the location of the moment center has to be along this line of action. If it's not on that line of action, this does not go to 0, and therefore we can't solve it. So the point that makes sense is right here, joint G, because that line of action passes through here. And in fact, a whole lot of stuff passes through there, doesn't it? 4 kips, GH, 10 kips, GD, They all pass through there. In fact, the only one that does not is the left-hand reaction, as well as member CD. So let's go back here, and we'll mark this as our new moment center. So this is joint G. So I'm going to do sum of the moments at G are equal to 0. And so now we're going to look at the rotations here. So the only thing left is the 14.5 kips and the force out here, P of CD, unknown, and we did solve this one, 42 kips. Not that it matters in this calculation, because that goes right through the 0 for the reference point, so it's 0 moment. So summing moments about G, I have 14.5 kips at this moment arm here, 10 feet. Relative to here, clockwise, therefore positive. And then CD at 10 feet. So P of CD is 145 kip feet divided by 5 feet. This is 5 feet, I'm sorry. $145. 29 kips. So very rapidly, when we use the summation of moments, we can find internal forces just with one calculation. It's quite a powerful technique. So now we're not quite done. Let's figure out here. Unlike the previous problem, this is not a zero force member, and so we want to calculate the force in that member, and it also will serve to verify our solution. So let's look at our free body diagram here. Where this is incomplete is that we have a force here. This is P of GD, and the thing I want to focus on is that it has a horizontal and a vertical component. We're ultimately going to want the true force in GD, but we can look at this in terms of horizontal equilibrium and see the vertical or horizontal component in that. So it's P GD horizontal and P of GD vertical. So if I sum forces horizontally, I have 4 kips positive going to the right. I have negative 42 kips. I have positive 29 kips. Plus the horizontal component of GD. That has to equal to 0. So P of GD, horizontal component, is going to be 42 minus 29 minus 4. Now let's look at these components here. Here's the true force, P of GD. This is the horizontal component. And this is the vertical. The nice thing about working with triangles is that once you know the angle or slope ratio of any side, then and the magnitude of one side, we can find all the other parts. So because the truss is 5 feet deep and the panels are 10 feet wide, that means that this is a slope of 5 on 10, or divide that out, 1 on 2. That means that the force vertically is going to be half of what it is horizontally. So we can do that by ratio if we want to write that out long ways. P of GD vertical is to the side 1 as 9 kips is to the side 2, or that means that PGD vertical is 4.5 kips. Now, every problem we do with this type of structure, in a sense, is self-verifying. So what I mean by self-verifying is that because these equations always balance to 0, that can be our check. So our final check here is sum of the vertical forces. Is that true? If we get 0, then we're probably right. So let's look at the vertical forces. I got 14.5 kips, 10 kips down, vertical force of PGD vertical, which is 4.5 kips, and a 10 kip load here. And that's all the verticals that we have, just those 3. And that's pretty easy to see. I've got a positive 14.5 kips right here, minus 10 kips, and then GD vertical, minus 4.5 kips. Is that 0? Well, that's easy to see. 14.5 kips minus 14.5 kips equals 0. It checks. So the final step when we ultimately get here is that we might be looking for the true force in GD. So for that we can use the Pythagorean theorem. Just take the square root of the sum of the squares. 9 squared plus 4.5 squared. About 10.1 kips. That would be our true force. We could also do this by ratio. If we take the ratio of, this is going to be a square root of 5. 2 squared plus 1 squared, square root of that, square root of 5. So this, we can take the ratio of 9 to the square root of 5 or 4.5 to the square root of 5. We'll still get the same thing. PGD is 10.1 kips. And that's how you do a more complex kind of truss, by breaking it down into the constituent components and summing moments about a central point. If you can understand that, you've got a good handle on moment calculations. That's all for now.